thank you very much for the kind introduction there. Again, I'm Paul Lipman. I'm Chief Revenue Officer at Infleqtion. Infleqtion is a quantum technology company. We span from quantum sensing, optical atomic clocks, and quantum sensors, all the way to quantum computing, both hardware and software. I'll let Pranav and Jeremy introduce themselves.
Great, nice to meet you all. I'm Pranav. I lead the software efforts at Infleqtion, and my route to Infleqtion went through the US Department of Energy. I did my postdoc at Argonne National Lab, studying applications for quantum systems to the utility sector and power sector. And that path has led us to become very close and understand how EPRI is helping to lead the utility sector into getting into quantum.
All right, and I'm Jeremy Renshaw. Lead our AI and quantum efforts at the Electric Power Research Institute, which is a nonprofit utility or a nonprofit organization that assists utilities with R&D. So we'll go ahead and get started. So I'm going to kick it off first, and so we're going to talk a little bit about capacity expansion planning, which really is what utilities use to plan for future energy demand many years into the future to meet hour by hour load shapes. So how much energy do they need, when do they need it, and balancing the different types of energy sources that we have to be able to maximize reliability and minimize the cost. So there's a lot that goes into balancing all these different factors, and there are many that I didn't include here. Things like projecting future energy policy that may affect what types of energy you may implement, whether it's a four-letter word like coal or something like renewables or nuclear or other advanced technologies. So utilities spend a lot of time and a lot of effort to try and get this right because there are very real costs of getting it wrong by overbuilding or underbuilding. And so to be able to explain this a little bit better, I would say AI caught a lot of people off guard in terms of the energy demand that it requires. So this graph shows a little bit of what the current and future demands are for AI for data centers. So the amount of electricity that they are projecting based on low, medium, and high. And what we're seeing is right now we're tracking along that high line, which no one had predicted 10 years ago. So a lot of utilities are trying to rush to catch up to meet this energy demand of data centers to be able to keep costs low and reliability high. So this is one of the reasons why it's really important to get this capacity expansion planning right. Similarly, you also have to plan for the type of load and when you have it during the day. So we're in a place like California where there's a lot of solar resources. So in the past, you've had what's called the duck curve of the energy demand throughout the day. It looked kind of like the shape of a duck. Here in California, we're seeing what we are now calling the canyon curve, where energy prices and energy demand can go negative. So if you think about this, if you're paying a lot of money to produce a commodity like electricity, and then you have to pay someone to take that electricity, that's a pretty bad business model. So we want to make sure to balance supply and demand for the utilities to get it right, but also so the customers don't have to pay in a regulated utility for over or under building. So it's a really important problem to get right, one that can make or break a utility company and therefore affect many millions of people throughout their service territory. So what we need to do is take advantage of all of the technologies that we have today, and you can see a number of different generation technologies here, everything from wind and solar to hydro, nuclear, and even battery storage. So being able to balance all of these to meet that hour-by-hour load years and years into the future, and also take into account what future energy systems might we have in terms of low carbon resources. So things like long duration energy storage, geothermal, advanced nuclear, fusion, things like that. So we are really looking at balancing all of this together, and it creates a combinatorial explosion of all the different possibilities you can have of, think about where you build, what type of grid you have, what kind of grid you need. And all of this together makes a very difficult problem, and one that I'm happy that we have people like Infleqtion to help us solve. So I'll turn it over to Pranav to talk a little bit more about that.
Great, thanks Jeremy. So Jeremy has set out what a challenging problem, an important problem, capacity expansion planning, CapEx planning is, and it requires new tools to solve the computational challenges of this problem. And so my goal here is to tell you a little bit about our work that we've been doing with EPRI in the past few months, with EPRI as our customer to help work together towards understanding where quantum technologies can intersect CapEx planning. And so the first part of our work with EPRI has involved understanding the state of the art. What software packages, what solvers, what mathematical techniques are being used for CapEx planning today. And that led us to a software framework called OpenTPs, which has emerged as the sort of industry standard benchmark for how capacity expansion planning is done today. And in particular, OpenTPs and other infrastructures for CapEx planning in the power grid rely on an algorithm known as branch and bound. And the best way to think about branch and bound is it's not quite brute force, it's smart brute force. At the end of the day, when you make a lot of decisions that are combinatorial in nature, you have this tree structure of what decision to take or not to take. And branch and bound basically makes intelligent decisions at that tree search. It will prune off branches of that tree. And so, importantly, while branch and bound is smart brute force, it does still boil down to fundamentally exponential scaling. And that's good news in some sense for any quantum approach, because we know that this problem is overwhelmed, especially when you take into account renewable energy sources that are distorting the grid, ditto for energy storage systems like batteries. These are all great things, but they make the CapEx planning problem much more computationally intense. And it's an area where the existing solvers through infrastructure like OpenTPs is really struggling. So where does quantum come in? Well, it turns out that the state of the art for quantum applied to branch and bound has changed dramatically in the last couple of years. And credit where credit is due, there's been great work done by University of Bristol as well as by JPMorgan Chase in terms of taking quantum algorithms and taking the same speedups that have worked in the past for generic brute force solvers and applying them to these smart brute force solvers, these branch and bound problems. And in particular, as a result of these advances, we now know today that quantum algorithms can attain and do attain what is known as a quadratic speedup over smart brute force. It was always known that they get an advantage that's quadratic over dumb brute force, but it's now known that these algorithms actually work over the state-of-the-art classically. And so this is a really promising arena for practical quantum applications. The key requirement to make this work, though, is to have very low overhead quantum error correction. And in fact, as you'll hear in Infleqtion's keynote tomorrow, this is an area where the industry is making dramatic strides. In our case, we showed with NVIDIA the first ever logical qubit applications using these technologies. And so I think in 2024, compared to even 2023 and certainly 2020, with the advance of algorithms that apply quantum computing to branch and bound, as well as dramatic improvements in quantum error correction detection and fault tolerance, we are at this unique era where problems like branch and bound do have the capacity for quantum speedups. And so the thing I'll leave you with is the upcoming work, which you should expect from the Infleqtion EPRI collaboration. What is next in the phase 2 of our partnership with EPRI is in 2025, we're going to be releasing an open source library that implements this quantum branch and bound algorithm. It's a really exciting algorithm, but there are no implementations of it in any sort of programming language out there. So we're going to put that out in the world for anyone to use. We're also going to make it tightly integrated with OpenTPs and these existing frameworks for capacity expansion planning, because we know that these kind of tools, for them to be productionized and put into utility, they need to be integrated with the libraries that practitioners use every day. So this is a preview of what's to come in 2025, and perhaps at next Q2B you'll hear another update on where this has gone. So that brings us to the end of the presentation part of this, and I'll pass it over to Paul Lipman to ask us some guided questions.
Great. Thank you very much, both of you. Pranav, first question for you. There's a lot of discussion, debate in the industry, including here at Q2B, about the utility of quantum computing in optimization problems, and specifically when and even if they'll have commercially relevant application. What's your opinion on this?
Yeah, you're right. The pendulum swings back and forth on this. In 2022, I think the mood at Q2B for optimization was somber, and anyone who was talking about optimization. You could bring your eggs, perhaps some of you did, and throw them. But 2024, I think the mood is quite optimistic about optimization. There's been a few key advances that have happened. Google did a phenomenal job of putting out a quantum algorithm called decoded quantum interferometry. And despite the name, which sounds very physicsy, it's actually an optimization algorithm for classical optimization problems. And it suggests a potentially exponential speed up for optimization. It's a very specific problem, but it does open this very exciting window into how quantum computers can take the hardest problems in the world, NP-hard problems, and not solve them exactly in polynomial time, that is, in efficient human-compatible times, but they can at least give a much better approximate solution than what the best classical optimizer software packages like Gurobi, OpenTPs, et cetera, can do. So I think that's one direction that the pendulum has swung back in, and of course, atop the dramatic progress that's made in hardware since Q2B last year, the previous year, I think it is now time to dare again and explore where optimization will actually work out for quantum computers.
So, Jeremy, turning now to the question of capacity expansion planning, what do you see as the economic impact of quantum computing in this area? And maybe even more generally, what do you see maybe over the next decade or so, the economic impact of quantum computing being in energy production and energy distribution more generally?
Yeah, that's a great question, and maybe building off of what Pranav said, getting this problem right or wrong can have a really massive impact, because imagine if you're building a $2 billion gas plant or a $10 billion nuclear plant. That's a massive investment for a utility. So to get that wrong and to build something you don't need can cost you billions of dollars that then you have to recoup from the ratepayers, which are all of us. Whereas on the flip side, if you don't invest enough, we've had other utilities that got caught where they were over-reliant on a single energy source. So going back to the 2022 war in Ukraine, gas prices in Europe shot through the roof, and we had a particular utility that we work with that was losing $125 million per day. That's in public record. So show of hands in the room, whose companies can afford to lose $125 million?
Per day.
No hyperscalers out there? Now imagine doing that for months on end. You're talking billions and billions of dollars in losses by getting this problem wrong. So now we can't necessarily predict future wars or energy crises, but having that optionality of resources to be able to minimize over-reliance on a certain energy source can have billions of dollars of impact.
So maybe then a question that ties the two of these points together. What are your thoughts on the time frame within which we'll see quantum computing kind of practically deployed at scale in the energy industry? And maybe I'll open that up to both of you.
Happy to start.
Yeah.
Throwing real surprises at us, thanks. So I think when we look at roadmaps, certainly for our own company, but other quantum companies out there, a key inflection point is year 2028. A lot of roadmaps align towards about 100, 200 logical qubits by that time frame. And these roadmaps are built on, today, real engineering and real demonstrations of getting to logical qubits. So that point seems to be the convergence of where we think there's the hardware's at the right scale, and it starts to outclass the world's best supercomputers, the world's best classical computing hardware setups. It is also important that 100 qubits, there are applications that run at that scale, and we are seeing that certainly in domains like material science. It may be that the first application is not necessarily capacity expansion planning, although there's certainly economic motivators for if you're going to lose $125 million a day, maybe we should prioritize that one pretty strongly. But we do feel that at that 2028 mark, there are material science applications, things like better batteries, better photovoltaics, which of course have dramatic implications for the energy sector.
Yeah, and to kind of go along with what Pranav said, I'm going to steal a quote from a good friend of mine who said, utilities line up to be fourth. So utilities are not going to be at the leading edge of this, so we might be a couple of years behind to work out the bugs because, to be completely frank, real people die when the power goes out. If it's in the winter, people freeze. If it's in the summer, people overheat. If it's any time, we can have deaths at hospitals and other critical infrastructure. So utilities are very rightly conservative to make sure that the power stays on at all times within reason. And so I would say we'll probably be a couple years behind others just to make sure that when it's ready, we're ready. But the incremental improvements that happen, I mean, I see those as they're ready. We can start to deploy those in small test beds and then scale up from there.
So Jeremy, maybe following on from that question, why was now the right time for EPRI to be engaging in this kind of quantum computing exploration with Infleqtion?
Yeah, so one of the things that we're really tasked with within the energy industry is looking at what's coming next and what value are we not taking advantage of now. And so what we're seeing is humans in general don't do well understanding exponentials. There's the old question that you ask a grade schooler of, you know, if you have a lake with a lily pad and then it doubles every day for a month, at what day was it half full? And most people say, oh, on day 15, but it's one day before the end of the month, day 29, day 30, depending on how long your month was. And people's minds just don't wrap around that well. And with quantum computing being an exponential technology, we realize we need to get involved now to prepare ourselves and the power and utilities industry to adopt these technologies quickly, because there is very real impact, not just in capacity expansion planning, but in so many use cases, hundreds of use cases across the energy industry.
Fascinating. I wouldn't have guessed day 29 for the lily pad. I'm going to have to kind of work that out on paper later on. Pranav, you've worked on a lot of quantum computing use cases around optimization. Were there any surprises or interesting findings that came out of your work on this energy problem?
Yeah, absolutely. And a lot of credit to EPRI as being this effective guide for not just us, but others in the quantum world to understand the needs of the power sector. I think one of the ones that has really stuck out to us is we've done, for instance, problem solving in the finance sector. Last year we talked about our partnership with JP Chase. And one difference between the problems that emerge in energy, power sector, versus finance is the so-called connectivity of the problems. If we're doing optimization of stock portfolios, every single stock is correlated in some way or another to every single stock. In the power sector, the problems are actually geographic in nature. A transformer in San Francisco doesn't have that much to do with a transformer in Michigan, but it does have a lot to do with the transformer in Oakland, for instance. And that actually ends up being a really useful feature for quantum computers, because quantum computers and quantum bits also have this kind of geographic locality and neighborhood phenomenon. And what we found as we were doing this resource analysis and resource estimation is that it's actually much better to work with these problems that are motivated by the real world, and I mean geographic real world, because those same aspects map very directly to the qubits in the system. And this is whether it's neutral atoms, superconducting, and so forth. So that was kind of a learning of where problem-specific optimization with folks like EPRI can take us to new heights of getting to solutions faster. And then I can also reflect just this today at lunch. We were having a conversation with the quantum interest group that Jeremy leads. And there's this reflection of the intellectual humility that is sometimes needed to make real problem solving happen, because half the times in traditional conversations between quantum experts and energy experts, the two speak very different languages, and it's hard to really convey what the problem is and what the solution is. EPRI has been phenomenally helpful in helping us understand the needs of the power sector. For instance, the scale of the problem, the fact that there's billions of dollars a day per stake, and also things like the latencies. Sometimes, unlike, let's say, high-frequency trading, it's okay to get a solution that takes 12 hours of runtime. And that's really helpful to know. There's other problems where you actually need the solution in a few milliseconds, and helping us understand that has been where this kind of co-design approach has unearthed new optimizations.
Great. So thank you for those really thought-provoking answers. I think we have maybe 30, 40 seconds left for any questions from the audience. Thank you for your attention during the session here.
No questions?
It's been a long day. Thank you all very much.
Thank you very much.